Oil and water are practically immiscible. In order to create an emulsion of oil droplets in water, we need to stir the mixture to create additional interfacial area. The energy requirement is gamma times the increase in interfacial area, where gamma is the interfacial tension between oil and water. Familiar emulsions that are edible include milk, salad dressing, mayonnaise, and there are several other emulsions used in the pharmaceutical and oil industries, and perhaps the most well-known example being emulsion paints. Generating emulsions requires a large amount of energy because of the high interfacial area between the bulk phase and the suspended droplets. And the energy inputs are typically using high-speed mixers. Today I talk about spontaneous emulsification. And to illustrate this phenomena of spontaneous emulsification, I consider a ternary mixture of water, benzene, and ethanol. Ethanol is considered a solvent because it's completely miscible with benzene. Water, on the other hand, is practically immiscible with benzene. The phase diagram is shown here. The green line is the binodal curve, and the red line is the spinodal curve. The area between the binodal and spinodal curve is a metastable region. In this region, we have a mixture of water, ethanol, and benzene that is completely miscible. Within the phase boundary, we have phase splitting occurring, where any composition here will split into two phases. For example, if we have a mixture composition denoted by M, it will split into two phases, A star and B star. A star is water rich and B star is benzene rich. How does spontaneous emulsification work? We take a homogeneous mixture of ethanol and benzene, say a 50-50 composition, denoted by the point here B, and bring that into contact with pure water. The mixture composition is M, and since point M lies in the two-phase region, it will split into two phases, and these two phases will have the compositions A star and B star. This implies that the water phase will equilibrate to A star, and the ethanol benzene mixture will equilibrate to B star. What is interesting is that the equilibration trajectories indicated in blue by these two lines, in this water-rich region, the equilibration trajectories end up in the metastable region between the binodal and spinodal curve, and therefore this will undergo spontaneous emulsification to produce droplets of benzene in water. This is the principle of spontaneous emulsification. This is also termed the Ouzo effect, and the reason for that I will explain in the next slide. Ouzo is an aniseed-based drink that consists of 45% ethanol, 55% water, and 0.1% trans-anethol. The mixture of ethanol, water, and trans-anethol is partially miscible, and the binodal curve is indicated by this green line here. This region defines the region of phase stability. This consists of a metastable Ouzo region indicated by this shaded region and an unstable phase splitting region. The composition of Ouzo is indicated by the yellow circle here. Adding Ouzo to water results in a cloudy dispersion that is translucent. Let's have a look. The important point to note is that the metastable dispersion is generated spontaneously, and therefore spontaneous emulsification to produce say nanodroplets or nanospheres is also referred to as exploitation of the Ouzo effect. Important characteristic is that the energy requirements are significantly lower, practically zero, as compared to traditional methods of emulsification using high-speed mixers. Further point to note is that the entry into the metastable region follows a curvilinear path. If the equilibration trajectory between Ouzo and water were to follow a straight line, the metastable Ouzo region will not be entered. In other words, a prerequisite of spontaneous emulsification and the formation of cloudy metastable Ouzo regions and dispersions requires a serpentine equilibration trajectory to be followed. The background theory why the equilibration trajectory is serpentine in character is described in my two papers that are listed here.